This is exercise 8 and we are group 8. I am Rowan Jaswal and today we would like to present our implementation on search algorithms on the game Sokoban.
My name is Dosi.
And I'm Spartian.
This is the table of contents for your reference. Introducing Sokoban. In the Japanese game Sokoban, the player is tasked with pushing boxes to designated storage locations within a confined warehouse environment. The strategic placement of boxes and the restricted movement capabilities of the player increases the complexity that requires proper planning and execution. Now we talk about the environment setup. Init initializes the environment for the matrix representing the level. This matrix uses numbers to represent different types of tiles. It initializes positions for various game elements using helper methods. Find position searches the matrix for the first occurrence of the tile type and returns its coordinates. Find positions, similar to find position, but returns all positions of a given tile as a set of tuples. Print level prints a text representation of the game level using predefined symbols for different tile types, aiding in debugging, and visualization in non-graphical environments. Show level uses matplotlib to create a visual representation of the level. Each tile type is colored differently to distinguish between walls, boxes, goals, and the agent. Next, we do the algorithm comparison. So for DFS, GBFS, and DLS, the optimality and the completeness is not guaranteed. But for the breadth first search, the optimality is guaranteed when step costs are equal, and the completeness is guaranteed for finite spaces. For UCS, the optimality is guaranteed, but the completeness is guaranteed when each step cost exceeds positive constant. For the iterative deepening for search, the optimality is guaranteed when step cost is uniform, uh, and the completeness is guaranteed. And for the asterisk search, the optimality is guaranteed, and the completeness is guaranteed when heuristic does not overestimate true cost. Next is the helper function. Is goal checks if the current state and satisfies the goal condition. Typically, all boxes being on goal positions get successes, generates all possible successes based on the current state by moving the agent in all four directions. Heuristic calculates an estimate of the cost to reach the goal from the current state. In Sokoban, common heuristics include sum of Manhattan distance from each box to the nearest goal. Reconstruct path backtracks from the goal to the start using a dictionary that tracks where each node came from, allowing the construction of the path taken.
Now, I'll introduce all the algorithms that we've used for our project. And these are the overall class that Rowan has discussed earlier. Now, and this is the environment that we set up for our game. Now I'll dive deeper into the search algorithms. Let's start with the greedy search. Greedy search is an algorithm that makes the locally optimal choice at each step with the hope of finding a global optimum. It selects the next step based solely on the heuristics immediate benefit, ignoring the broader consequence of the move. Next, A-star search. A-star search is an informed search algorithm that applies heuristics to find the most promising path to a target, aiming for optimal and efficient pathfinding.
Now I'll be talking about the remaining searches. So first comes the breadth first search. So BFS is an uninformed search algorithm that explores the neighbor's node at the present depth before moving on to nodes on the next depth level. It uses a queue for the same. Then comes the uniform cost search, which is a search algorithm that is used for traversing a weighted triograph, and it works by expanding the least count node. Next is the deep DFS. It explores as far as possible along each branch before backtracking, and it uses a stack to store the nodes. Then there is DLS. DLS is just another variant of DFS wherein it limits the depth of search to prevent infinite recursion. Right now, the depth is fixed at 10. Then comes IDDFS. IDDFS is the best of both worlds since it combines the space efficiency of DFS with the depth level completeness of DFS. Now I'll be talking about comparing efficiency. So as you can see, we have defined a function called run search algorithm, which takes in several parameters like algorithm, start, is goal, get successors, heuristic, max depth, and cost to quantify the different algorithms available for the input here. It first captures the current time, runs the specified algorithm with the provided parameters, and then measures the time once the algorithm finishes. It then calculates the total time taken, the path length, and the number of nodes expanded during each search. These metrics are returned in a dictionary format. What comes next is comparing optimality. Now, as you can see here, we have returned the time taken, the nodes expanded, and path length for each of the search algorithms. Now, for optimality, we have used the shortest path whichever results in the shortest path, that is the most optimal. So right now, as you can see, the most optimal is A star and BFS. So thanks a lot for listening.